Hello everyone. So today I want to introduce a new quantity to you. It's a quantity which is very useful when analyzing collisions, which is what we're going to spend pretty much the rest of the unit doing, right? Is analyzing what happens when two things interact with one another, whether that be long range or contact, right? But basically collisions between things. So, assuming you want to survive, okay, please no existential arguments about quality of life and things like that, right? Assuming you want to survive, would you rather be in front of this truck or that fast-moving truck? My guess would be the slow-moving truck, right? So this quantity has something to do with speed or velocity, if we want to be vectorial. What about this case? The truck, or at the exact same velocity, a bicycle. Probably the bicycle, right? What's different about them? Their mass is obviously different. Right? A truck's going to be much more massive than a guy on a bike. So when analyzing collisions, it's important to look at two things, mass and velocity. Together, these make up a quantity that was very important to Sir Isaac Newton, and it's called momentum. Momentum is denoted by a P with an arrow because it's a vector. Why isn't it an M? Probably because M's already mass, right? So it's a P, momentum. And kind of conceptually, momentum can be thought of as mass in motion. Okay, we're talking about collisions between things that are moving, mass that is moving. The basic equation for momentum is pretty simple. It's just the product of the mass and the velocity of an object. So momentum is mass times velocity. There we go. As we saw in our examples, right? More mass, more damage. More velocity, faster velocity, more damage. Right? So these are both just direct proportions with momentum. No need for anything complex, no squareds or anything like that in here. It is a vector. Right? Momentum has the same direction as the other vector in the equation, the velocity. So whatever direction the object's moving, that's the direction of its momentum. It can, of course, be written as an arrow, as all vector things can be if need be. Units come right from the equation. Mass, of course, is in kilograms. Velocity, meters per second. So momentum has units of kilogram meters per second. Now, there's no fancy derived unit name for this. It's just kilogram meters per second. Generally, anything more complex than this gets a special name. For example, a kilogram meter per second squared is a Newton. But a kilogram meter per second are just momentum units. So, how do the momenta of these two things compare, assuming they're moving here at the same velocity? And by the way, technically momenta is the plural of momentum, because it's Latin. Momentums, with an S on the end, is acceptable. All right, but momenta is probably more technically correct. You'll kind of hear me slip between one and the other. So here we have the truck and the guy on the bike. How would their momenta compare if they're moving at the same velocity? Well, if we're thinking of this in terms of a collision, we would assume the truck would have much more momentum. Why? Well, it has a large momentum because it has a large mass moving at a particular velocity. Whereas the guy on the bike would have a smaller momentum because he has much less mass moving at the same velocity. Like that, very visual, right? So less momentum here because of there being less mass. But we can also get differences because of velocity. So would it be possible for them to have the same momentum, even though the truck is much more massive? What would have to happen for the truck and the guy to have the same momentum, given that the equation is mass times velocity? Yeah, the truck would have to go a lot slower than the bike. Then, if it's enough, right, and this is very proportional thinking here, of course, nice concept builders and such, it could have a certain amount of momentum based on its large mass but its small velocity. And the biker could have the same amount of momentum with a small mass if it had a proportionally larger velocity. If the truck is 1,000 times the mass, the biker would have to be going 1,000 times as fast. And so it may not be physically possible, but theoretically it is, right, if you could go fast enough. And so just want to show you here that momentum depends on both mass and velocity. Now we're going to spend a bit of time today kind of dealing with the idea of momentum, okay, which in and of itself just seems like another quantity, mass and velocity. I mean, we've already had quantities like that before, but momentum, like I said, will get very useful for us when we start to analyze collisions, which is kind of the next thing we're going to do. So I hope you enjoyed this very brief little introduction to a new but important quantity, momentum.